All right, welcome to another episode of the Base-12 Book Club. I think we're on number 11 now. And in the last video, I left you with this diagram here. Actually, maybe first, just to let you know, we're talking about my book called Understanding Base-12 Math, How to Draw the Perfect Circle Using Dodecagon Geometry. So right now we're sort of progressing through the book. We're in chapter 3 where I'm introducing you to the Base-12 dodecagon, which is the new geometric pattern that I'm introducing to everyone that only exists on the Base-12 Cartesian plane, or it only exists with any significance on the Base-12 Cartesian plane. We can draw this shape on regular graph paper, and our natural inclination would be to approach it from a base 10 point of view. And when we do that, it's sitting outside of the length of 1. And when we switch to base 12, all those squares sort of shrink onto the length of 1. So that's something we've gone over already. The difference between base 10 and base 12 lies in the size of the decimal places. And it's a little bit misleading because on graph paper, of course, the squares aren't moving anywhere, so it looks like the 1 gets larger in order to accommodate the different sizes. But in actuality, so you can sort of think about it, the size of the decimal places is smaller. Like 1/10 is smaller than 1/12 is smaller than 1/10. All right. The real confusion with all this is when you're going back and forth all the time. If you just, once you get used to it, you just stay in base 12, then it's fine. Initially, we always want to go back and forth because we're like when you go to a country and you're learning the language, initially you're translating everything, but eventually you just speak the language and then it's fine. So we're getting there. But for now, we're still going back and forth, so sometimes it's a little bit confusing. So I do my best to keep it all under control. Okay, so I left you with this diagram last time. What I did is I connected all the dots that define the size and shape of the base 12 dodecagon, and you can see we got like a ring, 2 circles with an area in between. So we wanted to find out what's the area of that ring. So we know it's going to be in units of pi. So the area of a circle is pi r squared. That's the formula. So we're going to just find out what the radiuses are of those 2 circles and subtract the smaller circle from the big circle. So in our book, we go over that. We know what the radius of the outer circle is. It turns out to be the square root of 1.41, where we're adding 1 squared plus 0.7 squared in base 12. So 0.7 squared in base 12 is 0.41. And then we're going to figure out the inner circle. So the radius of that is 1.1 squared. The point that defines that circle is right on the x-axis, has the length of 1.1. So 1.1 squared is 1.21. Looks the same in base 10, but it's a different amount slightly. So we're going to subtract the square root of 1.21 from 1.41, and we get the square root of 0.2. So when we, pi r squared, so we square the square root, and it turns out that the area of that circle is 0.2 pi. So now we know. And so if we were to travel to each consecutive sort of dodecagon ring, we would be able to each time multiply by the square root of 0.2 by the next would be square root of 4, which is 2, basically by 2, by 3, by 4, by 5 as we go along. But we would do it in square roots and keep working in square roots. And we work a lot with square roots in this diagram. We're working with the square root of 2 for the perimeter of the dodecagon. We give the square root of 2 as the diameter. And actually that's the next thing we're going to do right now. We're going to draw another circle that's defined by the midpoint of the section of dodecagon that is perpendicular to the 45-degree line, or the 3-do-9-degree line in base 12. But I'm going to say 45-degree line, the section of the dodecagon that crosses that line, where those 2 lines intersect. We're going to draw another circle. That's what this looks like. So now we have 3 circles, and it looks like this circle is pretty much exactly in between those 2 circles. So we need to figure out what that radius is, and we do that actually on page 81 of the book, and we get the answer 1.306. So since you've got that equation, I'm not going to do it for, well, here, you can see it right there. That's how we get 1.306. And so we're going to subtract 1.306 from 1.4, and where I got it here, we get 0.106. So we do the formula, and that's the area of the outer circle. Now we got like two rings. So the outer ring has the area of 0.106 pi. And then we're going to subtract 1.21, or the square root of 1.21, from the square root of 1.306. And we get 0.0b6. A nice base 12 number there, pi. So now we're going to subtract 0.0b6 from 0.106. I think I'll just put all this up there, and we get an answer of 0.01 pi. So we can see that actually the outer ring of those two rings now is 0.01 pi larger than the inner ring, which makes sense because we have two rings that are in the middle, but the outer one's farther from the center. It's a little bit bigger. So that's how that all works out. So it's kind of interesting how it just works out nice. We got the length, or the area of 0.2 and 0.01, nice and simple. Something kind of beautiful about that, and that's where we're starting in our diagram. That's the innermost ring of the dodecagon pattern. And so I think we're just going to leave it there. Actually, the next step in the diagram is we're going to move to the fourth ring, and we're going to see how we go through the process of changing our irregular dodecagon, where all the outer points aren't the same distance from the center, to a regular dodecagon. How do we do that? And so we'll just go through that process and explore as we progress through the book. But I think that's it for this video. We just did some nice base 12 math. I'm going to try and start talking more in terms of base 12, or using the base 12 terms, like calling like the 10 a do, like a dozen. Okay, so that's where we're going. We're going to really make the effort to embrace base 12. I hope you can join me for this journey as we progress on how to build a diagram that separates the circle into 360 degrees using base 12 math or Dozenal math. So I hope you can join me for all that. Thanks for watching.